Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Lute Maleki, founder and CEO of OEwaves. We discussed the development of advanced quantum technology components, such as narrowband lasers, the company's origins at the Jet Propulsion Laboratory and its evolution, the importance of narrow linewidth lasers for precision and efficiency in quantum applications, and much more. We hope you enjoyed this episode. Hello, Lute, and thank you for joining me today.
Hello, Yuval. I'm happy to be here.
So who are you and what do you do?
Well, my current role is I'm actually a founder and currently a president CEO of a company called OEwaves, which may be familiar to a number of your audience, members of your audience. What we do here is that we are currently developing a number of capabilities to assist and enable and help the development of quantum technology. And that includes lasers and sources of entangled photons and stabilized lasers and systems that allow manipulating light and so forth. And it's important that to mention that this company has been around since 2000, and it was spun out of Jet Propulsion Laboratory. And I can tell you a bit of background on that if you're interested.
Yes, please.
Okay, back in 1996 or so, I ran a group at JPL that was a time and frequency research group. We were working on atomic clocks, and we had started working on something that was pretty unknown to the community at the time, but it was a quantum gravity gradiometer, and we were doing this based on the work that we're doing with the clock. And about the same time, of course, Shor algorithm was getting a lot of attention, and so people were talking about quantum computers. So I thought that it'd be a good opportunity to emphasize the work that we were doing related to what is now known as quantum technology. And so the group was changed the name and sort of somewhat of its direction to become Quantum Sciences and Technologies Group at JPL. And that I believe is the first group of anybody back in 1990s that was crazy enough to talk about quantum technologies. We were working on various different aspects of atomic clocks, laser cooling, all of that. And also we developed the Bose-Einstein condensate experiment, which is now its grandson, if you will, or grandchild, I should say. Granddaughter is on the space station, and that's the Cold Atomic Lab. And then we had some technology that was supported by DARPA and was in photonics. And so a suggestion was made that we should really, this is of interest to the community and the technology of generating microwave signals, reference signals with light. We were the first, we had invented something called the optoelectronic oscillator. And so based on that, we started the company back in 2000.
And as you look at your products today, almost 25 years later, what areas of quantum do you serve? Is it security or sensing or computing? Which ones?
Well, we are, I think, primarily sensing. However, I should say I'm kind of hesitant to say just primarily sensing, because we also support a lot of work in quantum computing, and we are working on technologies that would be of interest to quantum networks and that kind of thing in the future. So our aim is to really be and you heard the words before, the quantum picks and shovels, and we actually have a company that we are trying to spin out of OEwaves that's called Quantum Picks and Shovels, QPS, and the aim is to do exactly that, provide all the tools that are needed for all aspects of quantum technologies to grow and flourish.
If I remember your website correctly, you're doing narrowband lasers, right? Amongst other things.
Right.
What means narrowband lasers, and why do they need to be narrowband?
Well, yes, we are currently building the narrowest line width of any laser on the market right now. That is freestanding without being locked to any external cavity or something. Although it works by getting a diode laser and coupling it with what is called whispering gallery mode resonator, which there's interest, I can explain that. But this narrows down the laser line width or reduces noise of the laser with 6 orders of magnitude. And why is that important is that, number one, in many applications of quantum, the interest is to excite an atom or ion or any system to a very precise state. And that is precise in frequency. And that means that accessing this requires a very narrow line width, especially if you're doing this type of work. That the easiest way to explain that is the sensors is the clock transition, as it's called in the atomic clocks. In the atomic clock, the whole idea behind the clock is to use the internal state of the atom, and of course, how good the clock is has to do with how narrow that internal state is, so that its decay then would give you a very precise frequency. The narrowness of that state essentially directly translates to how precise the frequency that it emits is. And so people work very hard to operate with narrow atomic transitions in clocks and in a number of other applications. And so having a laser there is very important. But having a narrow line with laser also makes the system very efficient, even when one doesn't require that kind of a low noise to a set. The transition could be wider. For example, if there's laser cooling is involved and so forth, transitions for those states that are used in laser cooling are much wider. But nevertheless, what it does is it ensures that all the laser energy, if you will, is concentrated and is applied. So it makes the system much more efficient by using narrow line width lasers. So in conclusion, let me summarize that. The short answer to your question, in some cases, is absolutely a must, and in some other cases, it provides a capability related to improved efficiency.
I'm familiar with neutral atom computers, and neutral atoms also use lasers to excite them from one state to the other. But of course, there are multiple qubits, multiple atoms, and so laser power does not need to be just narrow, but also high power. What do you do about the high power aspect?
Yeah, the high power is something that really the only way to deal with that currently, depending on how high power one needs, is to amplify it. And yet again, this is where a narrow laser comes in, because the amplifier adds noise to the laser, obviously. And so if you have a low noise laser to begin with, then the noise of the amplifier added to it, you still end up with something which is low noise. So currently with availability of diode lasers, especially in the wavelengths of interest to neutral atom computing or any other kind of a quantum application. Really, the answer to higher power is simply some kind of amplification. And when I say amplification, I mean that in general sense. In some cases, we use actual amplifiers. In some cases, we can create an output from several lasers that are phase locked together, and nevertheless, you really can get that type of power that's required in certain application from a single laser.
So it sounds like you've been in the quantum industry even before Shor's algorithm, which is unique. But as you look at, say, the last year or two, what's new in your mind? What has surprised you, or what did you discover in the last year or two that you didn't know in the previous 20?
Yeah, I mean, it's you bring up the fact that I've been around before the Shor's algorithm, and that kind of dates me. But related to that is the fact that at the time when, as I said, my group was working on quantum science and technologies, we had people who were working on quantum computing, related areas. In particular, since we also were working on ion clocks, and the first activity towards quantum computing came from the work that was done at NIST with ion clocks. So we had the opportunity to sort of branch into that, but I thought that that's not going to happen in my lifetime. So I thought that wasn't the area that I was going to pursue. Well, so the surprise in the past few years is that, in fact, that's coming to fruition. And the surprise in the past couple of years is that not only is coming to fruition in the sense that, many groups and companies and so forth are demonstrating the capabilities, demonstrating that you can build quantum computers and then demonstrating its capabilities. But now they're seriously selling, companies are selling quantum computers. So that's a very pleasant surprise, I should say, because, foolishly, I thought this is going to take a lot longer. And so it's nice to see that actually it's rapidly evolving.
Are there export restrictions on your products? Is that a concern?
Currently, we don't have any export restrictions. As we move towards putting our products on PIC, photonic integrated circuits, then that becomes more of an issue. But currently, because we are not making them with PICs, despite the fact that everything that we have is quite compact, and in some senses, even we have products that are in packages that are the size of a PIC, but nevertheless, because they're not they're made with freestanding optics, they're not restricted.
Is the narrowband technology the ability to make the laser more efficient or with less noise? Does it apply across many wavelengths, or is it limited to a specific range of wavelengths?
That's a great question, and that's really where we come in and sort of approach this problem in a unique way. I mentioned to you that the way we get our narrow line width, or somebody called it ridiculously narrow line width laser, because it's sub-hertz in line width, is that we take a semiconductor laser and we couple it to something that's called a whispering gallery mode resonator. These are tiny optical devices which are only a few millimeters, less than 5 millimeters in diameter. And imagine if you look at your button on your shirt, it's kind of like that, except much smaller. But these devices are made, in our case, we make them out of extremely transparent material, crystalline material like calcium fluoride, magnesium fluoride. And as a result, we can excite modes in there that allow light to go around and around and around many thousands, millions of times, so that it works like a light capacitor, if you will. It sort of traps the light in there. And it's a resonator. And since it's a resonator, then it has modes, meaning that there are specific frequencies in which the laser can be, that can support, the resonator can support from a laser. Well, that feature, together with the fact that these very transparent material like magnesium fluoride and calcium fluoride, they have their transparency window goes from UV all the way to mid IR and so forth. So it's possible for us to take any semiconductor laser and couple it to this resonator and use another patented technology we have that everybody is now interested in using, at least in virtually all research associated with lasers on a PIC. Is called self-injection locking. So the light that comes from the laser and goes into the microresonator, this whispering gallery mode resonator, it sort of reflects back into the laser, and that locks the laser to the mode. So it's we don't need any extra electronics and so forth. So what that means is that, again, we can take any laser at any wavelength that falls within this very wide transparency window and suppress its noise. And that's exactly what we do. So the answer to the problem that you raised, which is all of these different wavelengths, is that as long as we can find a vendor that has a laser at that wavelength, then we can go ahead and build a laser that at that wavelength has extremely low noise. And that's really something that allows us to provide our customers with virtually any wavelength that they want. And this is important because semiconductor fabrication of the lasers is very difficult to be able to get lasers made in, across the whole band of wavelengths that are required for various different applications in quantum world. So the manufacturers of semiconductor lasers, they typically focus on a narrow band of wavelengths, and so they can extend the same epitaxy that goes into something that, at 15 nanometers communication wavelength to something like 795, which is for rubidium applications. So you have different vendors for doing that. It's not practical as yet to cover the whole thing. So that allows us to serve the community by taking these various different semiconductor lasers for various vendors and producing a narrow linewidth laser.
Would it make sense to make the resonator tunable? Is that a requirement sometimes?
We actually tune the resonator in 3 different ways. One way is that when if you were to thermally change the environment of the resonator, the temperature of the resonator changes, its dimension changes, its mode frequency changes. And since the laser is locked to the mode of the laser, as the mode frequency changes, the laser wavelength changes. So that's one way, and it's very effective, but it's thermally actuated, and so it's kind of slow. We also have, for very fast, much faster actuation, we apply a piezoelectric element to the resonator. And by applying pressure on it, we change the mode frequency, and that's very fast. It's as fast as you can do with a PZT. But then the range is rather small because the PZT cannot change the frequency over a few, maybe 10 megahertz or so, or 100 megahertz at the most. The third way, for applications that really require much bigger changes, we can also use resonators that are made out of electro-optic material like lithium niobate, lithium tantalate, and those, by applying a voltage on them, you can then shift the index of refraction large enough that you can move the wavelength a good bit, and that's extremely fast, of course. So yeah, depending on what the need is, we can address the requirements of the customer.
As we get closer to the end of our conversation today, I'm wondering if you could tell me a little bit about the company. How large are you? Where are you located? How are you funded? Anything that you're willing to share?
Sure. The company is located in Pasadena, California. As I said, we are an offshoot of Jet Propulsion Laboratory. And when we started, we were really a company that was doing a number of innovations for the Department of Defense applications. And we had a lot of DARPA work. We always have had DARPA projects from other DoD entities. And so we generated a large number of IP. We generated over the years more than 250 patents, of which currently about 100 of them are still available to us. And so the company then we back in about 2010 and 2014 decided that we wanted to address the commercial opportunities, and so we spun out a company that provided the first idea behind the LiDAR on a chip. And so that was acquired by General Motors. And after that, we decided that we were going to shift to products rather than working on just solely on projects and solving problems. But it's interesting that our size in terms of people has remained pretty much the same. We are about 32 to 35 people if you count some of the part-timers that we have. And we are now, as I said, our products are more than 60% of our revenue, whereas before they were a very tiny sliver of our revenue. So that has come since we've been focusing on products.
In last hypothetical, if you could have dinner with one of the quantum greats, dead or alive, who would that person be?
Oh, it's been my good fortune to dinner with a number of quantum greats, at least in the recent time. But the old ones, I think I would like to sit down and talk to Bohr, because I heard that in his dinner when he was having for his the reception for his Nobel Prize that he won, that he was so engaged in conversation that he was eating the dessert of one of the wives of one of his colleagues that was sitting next to him without knowing. And I would love to be talking to somebody that can get that engaged in whatever it is that he's talking about. So yeah, that would be kind of fun.
Wonderful. Luke, thank you so much for joining me today.
Thank you very much. Thank you for having me, Yuval, and best of luck.